Hello, everyone. My name is Scott Grizzard. This is Calculus 1, University of South Florida, regular calc, section 2, 22nd of April. Today, last time we talked about the definition of the Riemann integral. And today what we're going to do is we are going to go over properties of the integral, notations for antiderivatives, things of that nature, consequences of the definite integral being an area, properties of indefinite integrals, and a note on 1 over x. Next time, we are going to prove the fundamental theorem of calculus. Okay, are there any questions before we begin? Okay, so a quick word. I got some new toys. Let's see how they work out. Of course, I had the mic last time. That's new. I also got this... to stop the screen black problem, apparently will help it. I got this 4K Pro. It was the last video capture card in Tampa. I called around and found it, and it was the most expensive model available, because it's the only model available, and they only had the most expensive one left. So that's what I ended up spending my money on. Hopefully, I applied for a grant. Hopefully, that'll come through and reimburse me for it. That would be nice. So I got this new toy. We'll see how it works out. Hopefully that will stop the screen flicker black issue, because it takes the load off the tablet and puts the load on the processor of the computer that I use to play video games, which is, of course, the one I'm streaming from. And that, you know, as opposed to this little tablet thing, which has a wussy little processor and no cooling system, my beautiful desktop has liquid cooled stuff. You know, ultra cool, you know, it's an iceberg. So, you know, because of that, hopefully I will have, it will have much better, I'll have a much smoother experience. All right, so that's the only, there doesn't seem to be any questions in chat, so I will go on with the stuff. Let me see. Do I have my pen? Yes, I do. Do I have my backup pen? No, I don't. What happened to my backup pen? Nope, there it is. Okay. So, you know, pen, backup pen, just in case the nib breaks. Okay, so let's go ahead and let's start with the quiz from last time. Okay. So... I'm going to start with stating, like that. Start with the fundamental theorem of calculus. Now, here what I've done is I've defined it. We've got this new notation that we went over last time, okay? So because we went over new notation, I redid the notation for the fundamental theorem of calculus so that you can state it in integral format instead of just in the AUC format. Now, either works. You're perfectly fine if you did it the other way. I'm just stating what it is in both formats so you can see it. Okay. So the first is that, of course, G is if this right here, if F is continuous on D, and if G is any or an antiderivative for F on D, okay, that means that G prime of X equals F of X for all X and D. Those are equivalent statements. 1 to 5, how do we feel about the fact that this part of the statement, G is an antiderivative for F, is equivalent to G prime of X equals F of X? How do we feel about that, 1 to 5, the equivalence of those two statements? There you go. Perfect. All right. So you can use either one. Then for any base point A and for all X and D, fundamental theorem of calculus. Now I've rewritten it using integral notation, but it's the exact same thing. The derivative with respect to X of the integral from A to X, F of T dt. Notice that this is the thing that moves. This is actually static. This is the thing that's moving. All right, this is the thing that's moving, that X, right? Before the X was here, now the X is here, but this is still the thing that's moving. The derivative of this thing equals f of x. And the integral from a to x f of t dt equals g of x minus g of a. And that's the exact same statement there. How do we feel about that, 1 to 5? That these statements here are all equivalent. This is equivalent to the thing in orange next to it, and this is equivalent here to the thing in orange next to it, and it's also equivalent to this thing in purple, which I'll go over in a minute. Okay. All right. It's important to note that this right here is better notation for part 1 in terms of comprehension. This right here is better notation for part 2 in terms of comprehension, but they're both the same thing. Okay, the which one's better than the other? It's notation. What do you want? The notations mean the same thing. Sometimes people prefer one over the other. Okay, speaking of notation, Daffy Ducks writes this thing here. Does everyone see the problem here? Here I've got f of x dx, but I've got the x up here. Remember, x was frozen when I did this whole thing. Okay. So this is a little bit ambiguous. I can't have x here and x here. So what I need to do, and again, I said don't overthink it, I just need to replace this with a t. Okay. And what I wind up with is that this a and this a must match, this x and that x must match, that f there and the f here must match, and then the t and the dt must match. How do we feel about that, 1 to 5? Okay. And again, don't overthink it. It's notation, right? I can't have, this is ambiguous if I don't define it here. All right. Let's get rid of this right here. This is confusing. I don't care about that. All right. Okay. So here's what I've done here. I've used, so the compute the integral from 1 to x, f4t cubed dt. What do I do? Well, f of x is 4x cubed, g of x is x to the 4th. I apply the fundamental theorem of calculus part 2, and I get g of x minus g of 1, which is x to the 4th minus 1 to the 4th, which is just x to the 4th. I did here, I took my antiderivative, 4x cubed. My antiderivative was x to the 4th. I checked it to make sure that they were the same. And I wound up with that. So there's my answer. 1 to 5, how do we feel about this? This is my answer. Okay. Well, there is this weird notation in the book. And I noticed that people are asking questions, and I'm all for that. Please do. If you have any questions, ask them. Because if I ask questions and and you guys start typing, then we'll be sitting here for 20 minutes. So ask your questions as you have them, and then when I would normally pause for questions, I'll look at the chat. Okay. So are there any questions? Okay. So someone asked, so when we compute, we don't use Riemann sum. You can. You can do the limit as the Riemann sum, but you also have this tool called the fundamental theorem of calculus, right? So you can drag that out and use it. Okay. Now, about this notation over here, this is in the book, so I'll mention it here. This means evaluate g of t from 1 to x, okay? So this notation here means the following. This notation here means g of x Oops. It's doing that thing where it's not syncing again. So this is what that notation means, okay? G of t evaluated from 1 to x means g of x minus g of t. Okay? If I do x to the 4th, this is a side note. If I do x cubed evaluated from 1 to 5, okay? That's the same thing as saying 5 cubed minus 1 cubed. Okay? So that's a little notation. Absolutely, you can use integral notation. I am on board with that. So the question is, can we use integral notation? I assume you're meaning this right here for integral notation. And yes, is the answer to that question. Now this right here, x to the cubed, I'm not taking an integral here. I'm just asking what is x cubed from 5 to 1. So what I would say here is this. I would say that the integral from 1 to 5 of 3x squared dx equals x cubed evaluated from 1 to 5, which equals 5 cubed minus 1 cubed. And of course, I used FTC2 here, so I'm going to write it. Okay. How do we feel about that, 1 to 5? Right now, I'm asking about this kind of notational anomaly that you've seen in the book. Or that you picked up on, whatever it is, Nancy Pie or whatever it is you're watching, Khan Academy. Khan Academy I really don't like for integrals. Because Khan Academy likes to step on landmines and I like to sidestep them. Okay. And then how do we feel about this problem 1 to 5? This problem right here. There we go. All right. So we still got some concerns over using FDC2. If you come tonight at 5 p.m., don't forget 5 p.m. is the problem set. I'm sorry, the problem session. We'll talk about that some more, FDC2. Okay. All right, well, let's look at the Riemann sums. What I want is the 4 rectangles composed with the left endpoints. Okay? So the first thing I'm going to do is I'm going to state my points. My points are this one, this one, this one, and this one. Okay? This point doesn't matter. I don't care about it. I care about these 4 points here. How do we feel about that, 1 to 5? Okay. So let's look at this problem. Let's do something. Let's erase the stuff that I wrote here before. And let's do this problem together. Okay. Let's just get rid of it. Let's get rid of all the stuff about this problem and let's do it together. Okay. So here, my 4 points, the points I actually care about are this one, this one, this one, and this one. These are my 4 rectangles. Now, because I want left rectangles, I'm going to go from left to right. If what I wanted were right rectangles, I would go from right to left. But here I'm going to go from left to right. So my first rectangle, the height is going to be starting right here. So that's this rectangle here, because I'm doing the left endpoint is the height of the rectangle. My next one is this one here. My next one is this one. Now notice that this rectangle has no height. This rectangle has negative height. This rectangle has positive height. This rectangle has 0 height. How do we feel about this 0 height rectangle, 1 to 5? Okay. This is just a rectangle with no height. This last one's going to have negative height because I'm there. So let's do the negative. This is negative area. This is negative area. This is nothing. And this one is positive area. All right, how do we feel about the rectangles 1 to 5? I'm making rectangles based on the dots. I'm also doing the rectangles based on the fact that it's a left endpoint. That's the key here. I'm doing left endpoints. So what I'm going to do is I'm going to pick the left endpoint for my height. I'm going to read left to right. I'm going to read this left to right. Now, if I wanted right endpoints, I'd do the opposite. I'd go right to left. Right? If I wanted right endpoints, I'd be here. This one would be here. This one would have no height. And this one would be up here. But I wanted left endpoints. And now I'm going to compute left 4. Well, this right here, the height of that first rectangle is -1. I could have thrown it into the function, or I could have just looked at the graph and got, oh, look, the height of that's -1. Times the width, which was pi over 2. I took 2 pi and I divided by 4. The height of the next one is 1/2. And the height of this one is -1/2. And I can already see that those two are going to cancel. And then when I'm done, all I'm going to have left is -pi over 2. So there's a question about still being confused over why there's no rectangle for 0 pi over 2. There is a rectangle for 0 pi over 2, but that rectangle has no height. Okay? It has width, but it has no height. Its height is 0. The height here is -1/2. The height here is -1. The height here is +1. Here, I have a rectangle. Its height is 0. And then I wind up with -pi over 2. Now, I want the exact area. Well, if what I want is the exact area, I could either take a limit of this rectangle process, or I could just use the fundamental theorem of calculus part 2. And when I use the fundamental theorem of calculus part 2, I wind up with cosine here. There's my antiderivative. I check my antiderivative. And then I just apply FDC2 and I get blah, 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 algebra 0. How do we feel about what I'm looking for? When I say the exact area, I'm not looking for the area of these rectangles. I'm looking for the actual area under the curve. 1 to 5, how do we feel about what the question's asking? All right. And if you have any questions, please ask them. All right. Now, I can do all this algebra. I can apply FTC2, and I do all the work, and I get there. Or I could do something clever. I can look at this graph and say, wait a minute. This little tiny bit of area is going to cancel this bit of area here. And this bit of area here cancels that bit of area there. And I know that because I'm looking at the graph. Okay? Or because it's an odd function. So I'm looking at the graph, and I look at them symmetrical around 0. And I've got some piece here that's going to cancel that piece there, and that piece is going to cancel there. I'm going to wind up with 0 as the integral. The exact area is going to be 0. All right. Okay, so questions. Yes, the area under the curve. So the question is, so our area under the curve means to find the exact area? Yes. That's exactly what it is. How do I know that the height is 0? I know that the height is 0 because that's what f of 0 is. This height right here, f of 0, if I plug 0 into my function, okay, what was it? It was negative sine of x. So that's how I wind up with a 0 height for that. Okay. Yes, technically there should be a times pi over 2, but who cares? It's about to be multiplied by 0. Who cares? Now, if you didn't get the same antiderivative, there's someone that said that they got a different antiderivative than this. It probably worked out simply because it's symmetric. But if you got the wrong antiderivative, you got the wrong antiderivative. So I got to look exactly what you did to see what's going on there. But that is the correct antiderivative. I mean, you could have added a constant, but then you would have been subtracting the constant. So who cares about that? If your antiderivative was different, you got a piece of it. Are there any questions, other questions about that? Okay. So 1 to 5, how do we feel about part C now? There are 2 ways to do it. I either use FDC2, actually there are 3 ways to do it. I could take the limit of the sums. I could compute I could take FDC2, or I can just notice this little property that's going on here and be done with them. Okay. All right. Any questions anymore? All right. So please keep typing your questions into chat. I will, as I said, when I pause, I will be able to answer them. But I can't pause and wait for you to type them in. I just don't have enough time. Okay. So last time we talked about the definition of the Riemann integral through Archimedes. We talked about how Archimedes died. He was trying to teach calculus to a Roman centurion who just wouldn't stand for that sort of thing. Today, what we're going to talk about, we define the Riemann integral as a limit of Riemann sums. Today, what we're going to do is we're going to talk about properties of the integral. In particular, we're going to talk about 2 things. One, this connection between the antiderivative and the derivative. The antiderivative and the integral, or the AUC, gives us notation that's the same for both. Okay? And we'll do the notation, and then we'll talk about consequences of the integral being area and some properties of the integral that we get from that. And then we'll talk about properties of the indefinite integrals that immediately come from the properties of definite integrals. And then we'll wrap it up by talking about 1 over x a little bit, this nasty little function. Okay. If there's time, we'll also talk about dealing with finite discontinuities. There may not be. Next time, we're going to actually prove the fundamental theorem of calculus. Let's get started here. So let's give some properties of the integrals. First of these is notation. Let's do notation first. Okay. The first of these is the fact that there's notation in common for both. All right. For AUC, we do the following. We write the following. AUC FA of X equals this thing from A to X F of T dt. Well, because of that, we call this the definite integral. Well, because these things are connected, okay, we have this other thing. We have the definition for a new notation for the antiderivative. Let's see. And that new notation is the fact that f, this big F of X, equals this notation here. And this is called the indefinite integral. Okay. So let's do a quick example. Okay. The antiderivative of from 1 to 4 of 2 times x dx. Notice, because I don't have an x in the top here, I can put the x there. Here, I've got an x here, so I can't put an x there. Equals, well, the antiderivative of 2x, what would that be? Be x squared, evaluated from 1 to 4. Which equals 4 squared minus 1 squared, which equals 15. For the indefinite integral, I do this. I do 2x dx. And that equals this. There's no theorem because this is the symbol for antiderivative. And this equals x squared plus c. 1 to 5, how do we feel about that? It's new notation, right? The squiggly s thing, we can use it for both because these two things are connected by the FTC part 2. By the fundamental theorem of calculus, these things are highly connected, and therefore I can use the exact same notation for both. Okay. By the way, if you want me to talk again, there's this kind of aside, and please ask questions if you would, please. There's kind of this aside about the fact that there's this vertical line thing. And there it is. as soon as it appears again. Any questions? So there's the aside about the vertical line thing. Oops. All right. That'll make the notes neater. Okay, and now we've got some properties. First, and I cannot stress this enough, the definite integral is area. Okay? So there are times when I can compute the definite integral when I don't know the antiderivatives. Okay? Example. Let's do this from 0 to 1 of the square root of 1 minus x squared dx. Okay? How would I solve this? Well, let's see. How could I take an antiderivative? The square root of 1 minus x squared. What the heck is going to get? I mean, I could have. Oh, no, I can't do that because I can't do inverse sine because then I'd have 1 over that. And then if I took the derivative, no, that's not going to work. It's a mess. I can't do this, but it comes back to the fact that it's area. I have to use trig substitution if I want an antiderivative, and that's a subject for Calc 2. It's one of the first subjects for Calc 2, but it is a subject for Calc 2. But how else could I get at this? And the answer is, remember that this thing is area. Okay? So what is the thing that I've written up there? What is 1 minus x squared? And the answer is that's half a circle. The square root of 1 minus x squared. Okay? This right here is half a circle. Okay? And I wanted the area from 0 to 1 of this half circle. Well, that gives me this area right here. This is the area I'm talking about. Okay? How do we feel about that, 1 to 5? That what this thing shows is actually a quarter of a circle. And because it's a quarter of a circle and I want this area, here's 0. Here's 1. This is the area I'm talking about. Yeah. Highlighter's not much better. Give me the real highlighter. There we go. This is the area I want. Great. And then it moved again. Come here. Okay, it hates me. There's the area I'm interested in. I flunked kindergarten, so I can't even color inside the lines. And so what's the area? Well, 1/4 pi times the radius here, which is 1, squared equals pi over 4. How do we feel about that? 1 to 5. Okay. So for something to think about when you get home, or you are home, but we're remote teaching. Yes, remote, not online teaching, remote teaching. The dean was very specific about this. Okay, so there's some problems for home. All right. Second big property. I can add area horizontally. In other words, let A, B, and C all be in the interval D. Then I know that A to B, f of t dt, let's do A to C, equals the area from A to B, f of t dt, plus the integral from B to C, f of t dt. Example. Integral from -1 to 2 of the absolute value of x dx equals, yes. So that says I can add area horizontally. There's another question in here. Where did pi over 4 come from? Right there. I took pi, I multiplied it by 1/4, the 1 squared went away, and I wind up with pi over 4. So it was pi r squared times 1/4 because I was only talking about 1/4 of the circle. Okay. So here I've got this area. Well, what does this look like? This looks like a bunch of little things. So let's pull down our ruler here. Do a little axes. And of course, what we have is -1. So F looks like this. This ruler thing is cool. I like the ruler. And it goes up to there. And so what I want to do is I want to compute the area under the curve. And I want to go from -1 to 2. Well, how do I compute that area? Well, what I want is, oops, this is going to be like mega thing. I want really small one now. I want this area here and this area here. So how do I do that? Well, I want to compute that area. So what do? Well, just add them. All right, I compute the size of this triangle here, and I compute the size of that triangle there. This triangle right here is going to be 1/2 base times height. Or I could do the definite integral of -x, and then the definite integral of +x. Right? Because this is really a piecewise function. Remember that? So what I can do here, this equals the integral from -1 to 0 of the absolute value of x dx plus the integral from 0 to 2 of the absolute value of x dx. Well, this one is all positive. I'm sorry, everything in here is negative or 0. So that means here, I do here the integral from -1 to 0 of -x dx plus the integral from 0 to 2 of x dx. And I could do the whole, antiderivative. So if I wanted to do FTC2, because I just can't help myself, I could say, well, the antiderivative of this is x squared over 2. So this is going to be x squared over 2, negative x squared over 2, evaluated from -1 to 0, plus x squared over 2 from 0 to 2. And this is just because I can't seem to help myself doing this. And this is going to be 0 over 2 minus -1 squared over 2 negative plus 2 squared over 2 minus the other side, which was 0 squared over 2. This is going to be -1 squared. Those two negatives cancel. I'm going to wind up with 1/2 plus 2 squared over 2, 2. Or, I could have said this area has 1/2. This is a triangle of, ooh, I just messed up somewhere, didn't I? Nope, that's right. This is an area of 2, and I wind up with 2.5. How do we feel about that, 1 to 5? All this says is that I can break this up horizontally. Okay. All right. Another consequence of this, the fact that areas are this, is the following. I can add area horizontally. I can add areas vertically. Now let's do another one. Let's do this one. Add areas vertically. Okay. So let's do an example. Actually, this should be an example color, shouldn't it? There we go. I can add areas vertically. All right. A to B, f of x plus g of x dx equals integral from a to b f of x dx plus integral from a to b g of x dx. Okay, how do we feel about that one, 1 to 5? Okay. I want you in green. There we go. Example color. Well, let's do an example. Let's look at the, Control Z, select, put you in green. There we go. All right. Well, let's look at an example here. If you're wondering why the thing is jumping, it's because I'm taking things off the main computer and I'm posting them here on this thing, and the takes a moment to sync. Okay. Let's look at an example of that. I had before this lovely function here. Let's add 1. And what did that do? That just shifted it up 1. Correct? So now when I do my area under the curve, I'm talking about all of this. That's not it. Oh, there's no snippy tool on that side. There it is. Okay. There we go. Let's get rid of the stupid drawing and let's put on a real drawing. So what I'm going to do here, if I'm taking the area from -1 to 1, okay, which is the full half circle, which is not what we did before. What I'm going to do is I'm going to take this area here and this area here. So what I'm saying is the area of the circle plus the rectangle is the area of the circle plus the area of the rectangle, or the half circle in this case. So the area of the whole is nothing but the area of the two parts. How do we feel about that, 1 to 5? Okay. Okay. All right. This has an immediate consequence for antiderivatives. Remember the FTC1. Yeah, I'll just put FTC1. That's just confusing. So FTC1 says that all antiderivatives are really just AUC functions of some sort, or area functions. So that means the following. That means that the integral, the indefinite integral, or the antiderivative of f of x plus g of x dx equals the antiderivative of f of x dx plus the antiderivative of g of x dx. Okay. That's just an immediate consequence of the fact that the thing's true. That antiderivatives are area under the curve functions for some base point. Okay. Another consequence, no width. Okay. What does that mean? My function has no width. That means and we've already seen this before. I already mentioned it before. That means that from a to a, f of t dt equals 0. I got no width, I go nowhere. Okay. Another one we also saw before was switching the endpoints. How do we feel about the no width and switching the endpoint rules? I've already talked about them. I talked about them last time. How do we feel about them? 1 to 5. I think it was the time before lost. Okay. All right. So let's talk about a few others. Go away. Definitely go away, you. The next one's the constant multiple rule. Okay. So for an antiderivative, it's the same as a derivative. Right? From the derivative rule, we have the following. I'm going to use constant. I don't want to use C. Somebody give me, and I don't want to use A, and I don't want to use B, and I can't use D. So somebody give me a constant that I could use. I'm out of letters that can be constants, can't I? Let's say constant. Q, P, P. I like P. Okay. But P means prime, so don't let P be prime. W, X, Y, and Z I don't want to use because they're Chapman-Lee variables. Okay. So then I have that P times f of t, I'm sorry, f of x dx equals P times f of x dx. Right? And that's from the constant multiple rule for derivatives. Well, that gives us the following immediate consequence for antiderivatives. For AUC, that gives us the following. How do we feel about that 1 to 5? Okay. Ooh, I get another property that I didn't get in the last class. Makes me happy. I didn't get to this one in the 9:30 because I ran out of time. All right. Here's another property. Okay. Move the ruler. Yes, I can actually get rid of the ruler. All right. If the limit as x goes to b, right, I need f to be defined at b, not necessarily continuous. Okay. Let's do it like this. Let's keep it. Let's do it like this. Okay, so let's actually make it continuous at b. Okay. Now, there's another consequence of this, and that is the following. Okay, and I should put a little star next to this because this isn't on the test. Okay, technically this is Calc 2 stuff right here, and the reason why I'm mentioning it is because this is how you deal with continuities. So this lets you deal with finite and finite jump discontinuities. Okay. And your book does this huge thing about the fact that you can do this, but the idea is this. And again, I don't want to spend too much time on it because I got to get to the 1 over x thing. But the idea is this. Okay. If I've got f of x, f defined on f continuous, f defined on a C with a jump discontinuity at B. Okay. Then I can deal with the discontinuity. So let me show you how. So let's do F example. F of x equals the function 1 for x if x is less than 0, and 2 if x is greater than or equal to 0. So what I've got here on this function is I've just got a jump discontinuity, right? So here's my function. Oops. Here's my function here. I've got a hole here, and then I've got a jump here. Okay, and the way that I deal with this, so then the integral from f of x dx from -1 to 1 would equal the, here's my jump. My jump is right here. So what I'm going to do is I'm going to do f of the integral, the limit as x goes to -1 of the integral from -1, sorry, x goes to 0, which is the breakpoint, -1 to x, f of t dt, plus the integral from 0 to 1, f of t dt. In other words, I can just take the area as if this thing didn't exist, and the area of this as if the jump didn't exist, and add them together. How do we feel about that 1 to 5? It's a technical detail. The book kind of glosses over it, saying, "Oh, we'll do partitions and stuff." And who cares, right? This is actually what you're doing. What you're doing is that you're kind of just adding up the pieces, and you're taking the what's called an improper integral, like you care, to that point. So basically what it says is I take the limit of the thing and I just call that the piece. Again, not on test. This whole bit is not on the test. But it's how you deal with jump discontinuities. A finite number of jump discontinuities. If I have an infinite number of jump discontinuities, I may not have an integral at all. Okay. Let's mention one other thing. I've got 7 minutes left, I think, if my math is correct. No, I got a few little less. I must have started late. Let's talk about one other thing. Let's talk about 1 over x. Okay. In this class, in particular, in my class, antiderivatives are only defined over intervals. Okay, so your book does this thing, and it's the one thing that he does that James Stewart does. I mean, even more than putting graphs of the derivative and the function on the same place, because I get that. That's, it's more efficient for printing. This is the thing that pisses me off that he does most, and it's wrong. I mean, it's technically wrong. Okay, this idea of antiderivatives. Antiderivatives, the reason we give a crap is the fundamental theorem of calculus. Okay, antiderivatives are only defined on intervals. Okay, so let me give you an example. Here's what's in the book. Okay, the book says the antiderivative of 1 over x dx equals the natural log of this. Okay, now what's the problem with that definition? The problem is this right here. I do this. Well, then what's the antiderivative from -1 to 2 of 1 over x dx? The problem is that then you go FTC2 and you say, oh, okay, well, I do ln of the absolute value of 2 minus ln of the absolute value of -1. And that means that this is just ln of 2 minus ln of 1. And what's the natural log of 1? 0. Ln of 2. What has he done there that is just absolutely horrible? He doesn't do this bit. He doesn't do this. I'll give him credit. He does not do this, but he does do this. Now, what's the problem with this definition? What's the problem with this statement here? What did I do? What does the graph of 1 over x look like? Here's the problem. This bit right here is -infinity. That area there. This bit up here is +infinity. I just took infinity over infinity. I just took I actually did infinity minus infinity. What I actually did was the integral from -1 to 0, ln of, 1 over x dx minus 0 to 2, 1 over x dx. Sorry, this should be 0 to 2. Plus -1 to 0. It was better the way it was. Oh, you can't see it because you're still looking at the graph. Ah, that's nice. You can't see me making a couple of mistakes here. Okay. What I actually just did was this. Okay, and I can't do that. Okay, that is wrong. That is a big no-no. Okay? So, for our section, if you see the antiderivative of 1 over x, okay? If you see the antiderivative of 1 over x, you need to ask where. Okay? How do you feel about this 1 to 5? This is a little freaky. Okay? But this is the landmine that he invites you to step on. Okay? He invites you to step on this landmine. Now, he doesn't step on it himself, but he doesn't warn you about it, and he doesn't really, by calling antiderivatives things that can be defined where I don't have an interval, okay, he's inviting you to step on this landmine, and it's wrong. Okay? So for an R class, okay, and this is how it'll be on the exam because yours truly wrote it. For R class, if I ask you for an antiderivative for ln of x, I'm only going to ask you. Now, what's fine is this, right? Fine. I could ask you for the interval from 1 to e of 1 over x dx. That's fine because I'm not crossing 0. That's okay. But I can't do the other one. I cannot cross 0 with this antiderivative. Okay? So for our class, we don't care about this. This ln of absolute value of x, gone. Bye. See ya. Okay? This ln of absolute value. It's now you can use this ln of absolute value of x because that's equal to these two things on the domain. But the point is that I can't cross 0 with an antiderivative. I mean, I can't cross discontinuities or places where the function is not defined, especially discontinuities of the second degree with an antiderivative. I really need these things to be continuous over an interval. Are there any questions? 1 to 5. How do we feel about that warning? I think there are only 3 people left that are actually watching this stream. Okay. All right. So that's it for today. I went over properties of the integral, notations for antiderivatives in the indefinite integral, consequence for definite integrals being inner areas, and properties of indefinite integrals from definite integrals and definite integrals from indefinite integrals. And then I warned you about that landmine 1 over x. The next time we're actually going to prove the fundamental theorem of calculus, and I will have notes that I'll be giving you ahead of time, very nice notes and stuff like that. After the fact, I'll post notes that are actually very nice on this as well. Any other questions, comments, issues, suggestions, or thoughts? Okay, well, in that case, I'm going to stop streaming. I ran 4 minutes over. I actually didn't. I ran 2 minutes over, but then I was 2 minutes late. And I will see you guys. Remember, tonight is the problem session at 5 p.m. In Discord. I will see you guys later.